Hi. I wonder, are you in a light-polluted city and have a monochrome camera? Maybe you want to make your images look like true RGB images. Or maybe you're interested in getting a monochrome camera and do narrowband imaging, but the Hubble palette is not quite what you want. Well, I've got a solution, and it uses HA, OIII, and S2 filters. It's super easy to implement. You just need to know 3 numbers from your camera and then copy and paste some equations into Pixelmath and Siril. I will give you those equations. Big shout out to astrophotographer Tim Hutchinson for coming up with this. For this tutorial, you can go to my Discord and download the data to process it yourself. Welcome to Deep Sky Detail. Okay, so this image here was made with a monochrome camera and S2, HA, and OIII filters. It's based on Pixelmath created by Tim Hutchinson, who gave a presentation for the Astro Imaging channel. I'll link the video below in the video description, but the gist of Tim's idea was to examine the emission lines of 3 gases that we're interested in and add them proportionally to the RGB channels based on how much they should theoretically contribute to each channel. Here, let me show you an example. These are the emission lines for hydrogen. When I take a narrowband image with my hydrogen alpha filter, I'm really just measuring where the hydrogen is glowing. You can see though that hydrogen emits light in the red range, which the hydrogen alpha directly filters, but it also emits a bit of blue, cyan, and purple. Because of that, Tim developed a Pixelmath formula that splits up the hydrogen filter's light into the 3 RGB channels. It's pretty cool. The result is a picture that pretty much resembles an RGB image, so let's get into it. Sometimes when I do narrowband imaging, I might start out by going to image processing and RGB compositing. I then put S2 in the R channel, HA in the G channel, and OIII in the blue channel. You can see that the blue dominates because the OIII filter lets in more light pollution than the other filters. So we could do a background neutralization by going to image processing, color calibration, and selecting part of the background. Then click Use Selection and Background Neutralization. Now the image makes a lot more sense as the green HA dominates the other filters. We could then do some tone mapping and get it to the Hubble palette, but instead of doing that, I'm going to go to Image Processing Pixelmath. I've already stacked my S2, HA, and OIII images. To load them into Pixelmath, just click the plus button and find the correct images. When they load, you'll see their variable names here. Because I stacked them with Siril and Cyrillic, it already knows their names. But you can double-click this to change them to whatever you want. For example, you could double-click this and write something strange if you'd want to. But now, every time you use this variable in an expression, Siril will know to use the pixels in the corresponding image as the variable. Now, part of the formula includes finding the quantum efficiency of your camera for each filter that you imaged with. So in my case, I have to find the quantum efficiency of my camera when it is imaging HA, S2, and OIII. Quantum efficiency just refers to the camera's sensitivity. If it is 100%, then any photon that hits the sensor will be registered as an electron for your final image. If it is 90%, then 90% of the photons that hit the sensor will be detected, and it keeps going. I know that my camera has a peak quantum efficiency of 90%, but that does not mean it has 90% efficiency for everything. What we want to do is find a graph that shows the quantum efficiency of our camera at different wavelengths. I found the correct graph for my camera here. Keep in mind that some of the graphs out there use relative quantum efficiency, where the peak of the camera is always 100%. That's probably the wrong graph to use. Try to find the correct one where the peak in the graph corresponds to the specifications stated on the camera's website. See, this graph peaks at 90%, which is the same as what the manufacturer says. The HA emission line is 656 nanometers, the OIII emission line is 501 nanometers, and S2 is 672 nanometers. I want to find the quantum efficiency for each of these filters. So for HA, I'll estimate where 656 nanometers is on the graph. It's about here, and go straight up until I reach the line for my camera, the ZW0294mm. It looks like the quantum efficiency is around 75% or so. You don't have to be exact. Just get it in the right ballpark. For S2, the emission line is at 672, which if we go straight up is about 67%, and OIII is around 89%. I've written these down as proportions, not as percentages, and that's important. You'll notice how I named these expressions. Each filter just has a qe in front of it to indicate to me that it means quantum efficiency. I'm going to put these three expressions into Siril's Pixelmath parameters section separated by commas. You'll notice that I have an expression for H-beta. I don't have an H-beta filter, but if you did have one and wanted to use it in these formulas, I'd refer you back to Tim's presentation on the Astro Imaging channel to figure out how you do that. But imaging with H-beta is pretty rare and not needed because HA generally shows everything and more that H-beta can do. Now for the fun part. We want to put these equations into the corresponding RGB sections of Pixelmath. There is some debate about whether to use the sum of the max values in these formulas. Again, I'd refer you back to the original presentation for why the max is generally preferred, or the maximum is generally preferred. And I find that this second set using the maximum is generally better. Let me go ahead and copy and paste these into the sections and then click apply. Let me reiterate that you want to find your camera's quantum efficiency for these parameters. Okay, once I click apply, a new image should appear. I'll go ahead and perform an auto stretch. Now the image is really pretty green, and that's expected. The OIII filter dominates green in these formulas, and it is also the filter that lets in the most light pollution. So we can go ahead and do a background neutralization. Go to Image Processing, Color Calibration, make a selection of the background and click Background Neutralization. It has done a good job at neutralizing the background and making it look like an RGB image. We can now close the Pixelmath equations. There is still some green noise, similar to if you were actually doing a real RGB image, so we can get rid of that by going to Image Processing, Remove Green Noise. There are still some slight gradients, so go back to Image Processing and click Background Extraction. Make sure RBF is clicked, as well as Add Dither, and make a few selections around the image. Then click Compute Background and play with the smoothing slider or add more sample points to make things perfect. That looks pretty good to me. Let's click Apply. I'm going to crop the image a bit and turn off the auto stretch. Now it's time to manually stretch the image. I'll stretch it to where the stars are where I want them to be and then run StarNet++ to remove the stars. Then I'll stretch the nebula a bit more and save the image as a TIFF. To get started stretching, go to Image Processing and Generalized Hyperbolic Stretch Transformation. We'll zoom in on the histogram and select a symmetry point on the right-hand side to begin with. Move the local stretch intensity slider pretty high and start stretching with the stretch factor until we see the nebula. That's pretty good for our first stretch. Click Apply. Now let's zoom out the histogram by clicking the 1, and we'll repeat the process, but this time using a logarithmic scale. And we'll set the symmetry point somewhere in the middle of the steep curve here. We'll increase the local stretch intensity slider a bit, and then increase the stretch factor and click Apply. We could keep stretching a bit more, but I don't want the stars to get too much bigger than this, so I'm going to run StarNet++ in the data to remove the stars and stretch the nebula separately. If you have StarNet++ set up with Siril, go to Image Processing, StarNet Star Removal. What we want to do is make sure pre-stretch linear image is turned off, but recompose stars on completion and generate star mask are checked. Then click Execute and wait until it finishes. Okay, so it has finished, and two histograms have popped up. One for the nebula on the left and one for the stars on the right. We can now start stretching the nebula independently like we did before. I like using the log scale and keeping this curve as straight as possible. Choosing the correct symmetry point is crucial. Every now and then move the black point slider up a bit to darken the background and click Apply. I'll do it in an iterative process until I'm happy with the amount of nebulosity I see. This looks pretty good. I generally like Orion's core a little bit brighter. I know that some people like to do a so-called HDR image. Doug from Astro AF just did a video on it. I'll link it in the description, but my personal preference is to keep the core bright. I just think it looks nicer, but I'm a bit weird. So I'll go ahead and close the histograms and save this as a TIFF file. So here it is in GIMP. I like this image. Here's the first iteration I did, and this is the one we just did. I like the colors in this second one a lot more. They seem more natural. The difference has to do with the fact that I did not do a photometric color calibration with the second iteration. I did do it with the first. I like the second more, I think. Zooming in, it looks nice, but I think we could make it a bit sharper. So let's open it up in AstroSharp and sharpen things up. We'll then use AstroClean and combine the sharpened and clean images in a cool way to make sure we don't lose the detail from AstroSharp. Okay, here's AstroSharp open. The first thing I'm going to do is change the model to dual PSF. Then I'll open the image. The thing that's nice about the dual PSF model is you can control the sharpening of the stars and the deep sky objects separately. Generally, the DSO can be sharpened a bit more than the stars, so it's nice to be able to do that. Before we start sharpening though, let's check the star mask. Let's quickly change the model to star mask. The star mask tells AstroSharp what are stars and what isn't. We want to make sure it's working correctly. It looks like there are a lot of false positives, so let's change the star sensitivity. Increasing it will decrease the amount of stars it detects. There we go, that's a lot better. We could even try 99.5. We can also change this first blend parameter to something like 2. This will help the stars blend in better when the model combines the stars and nebula. Let's go ahead and change the model back to dual PSF and click Update Slider. Okay, let's quickly open Siril real quick. I'll go ahead and select a star. You can see that the full width half maximum for this star is around 7 to 8. I've actually done this with several stars, and it seems that the full width half maximum is around 6. That will help us determine what the values for the PSF slider should be. With the dual PSF, we can actually use the full width half maximum for the DSO slider. But the stars will look funky if we use 6 for them. So a good rule of thumb is to divide the full width half maximum of the stars by about 2 to 2.5. When we do that, the PSF should be around 2.4. Let's use 2.5 for the stars. We'll use update sliders to get a preview. Okay, so we are getting some ringing around the stars, but not all of them. This probably means that we need to blend things in better. Let's decrease the first blend parameter a bit more. I'll change it to 1. If some of the stars aren't blending at all, but others are, try lowering the star sensitivity, decreasing the blend 1 parameter, or increasing the blend 2 parameter. For this image, these parameters worked well. Now I'm going to scroll around the image to make sure things are working okay. Yeah, that looks nice. I'll go ahead and click multi-core and update sliders and then click full image. I brought the images into GIMP to compare. Here is the sharpened image and here is the original image. Let me blink it in and out. Before sharpening and after. Before and after. Now AstroSharp can have a bit of trouble when things are really bright, so I've masked some of the stars in the brightest areas of the nebula. Here's the mask. Let me turn off the mask so you can see what's going on. There's just a little bit of ringing, but it goes away nicely when masked away in GIMP. But all in all, I think it has sharpened things nicely. I'm going to create a new TIFF image from this file. Let me flatten it and call it something like Final Sharpened Image. There's also a bit of noise, so let me bring this into AstroSharp again and run AstroClean. Here is AstroSharp. I'll change the model to AstroClean. I'll run it at 100% aggressiveness because we can bring it back into GIMP and manipulate things a bit more. Here is the preview. Let me click full image and wait for this to finish. Alright, we're back in GIMP. Here's the sharpened image, and here's the clean image. AstroClean is very aggressive. It can blur some of the nebula. And the most noisy parts of the image are in the darker areas. So what we can do is mask the AstroClean image to only show up in the darker areas. Let me show you how to do that. First, right-click on the cleaned layer and select Create Layer Mask and choose Full Transparency. None of the cleaned image comes through now. If we click on the layer mask, not the layer itself, and start painting the layer mask white, the clean layer will start to show through. Holding down Alt and then clicking the layer will show us the layer mask itself. There's a smarter way to do this than just painting it in. Let's select the sharpened layer and copy it. Then click on the layer mask of the cleaned layer and paste using Ctrl V. Right-click on the new floating layer and anchor it by pressing Anchor Layer. Let's make the layer mask visible again by holding down Alt and selecting the layer. So here it is. What we want to do is do an extreme curves adjustment so that the whites and grays are basically white and the background is black. We can then invert the layer mask. The darker areas will have little to no noise reduction. while the lighter areas will have aggressive noise reduction. Now there is quite a sharp transition between the noise reduction portion and the no noise reduction portion. So we can click on the layer mask and add a Gaussian blur to it. That looks pretty good. Let's pan around and check our results. I think it looks nice. I've uploaded the data to Discord so you can try this technique. I bet you can do better than me. Please subscribe and thanks for watching.